action potential. Calcium floods into the cell via those fast calcium long-lasting channels, and as they do so, they flow through gap junctions into adjacent atrial contractile cells, right? Or if we're talking about the conduction myofibers or the bundle branches, they flow into adjacent ventricular cells. And so now we're going to look at the action potential of the cardiac muscle cell, which is more similar to what you're used to seeing with the skeletal muscle cell. Right? So we find those atrial contractile cells here in the atria. We find the ventricular contractile cells down here in the ventricle. But the appearance of the action potential is very similar between the two. Okay, may I erase the board? You guys have that? So here is the skeletal muscle action potential. Here's the cardiac muscle action potential. What's the difference between the two? There's no gradient potential in the heart muscle. That's because each heart muscle is receiving its trigger via the gap junctions of the previous heart's muscle's action potential. This is actually most similar to a nerve axon propagating action potentials from the previous voltage-gated channels. As an action potential propagates down the nerve's axon, we don't have ligand-gated channels along the way. It's the voltage-gated channel opening that sends a flood of potassium and it opens the next voltage-gated channel. So again, we spike that threshold right away. We don't see that preliminary action potential. For the same reason, that occurs with the contractile cell. Okay? So unlike the autorhythmic cell, we have a resting membrane potential, created by the same factors that do it in muscle and nerve. The sodium-potassium pumps, the leak channels for sodium and potassium, the proteins that have negative charges give us a negative resting membrane potential, a little bit lower, it's closer to 90, but a resting membrane potential. Then, the flow of calcium, because of our fast-gated, long-lasting calcium channels, the flow of calcium from the autorhythmic cell, or if it's adjacent contractile cells, it will be the flow of sodium, will flow into the cell via gap junctions and will reach the threshold, and we will see the first depolarization occurring for an action potential. These are due to voltage-gated sodium channels. Exactly the same reason we have for skeletal muscle. Our autorhythmic cells are the ones that were different because those were voltage-gated calcium channels. Okay? These are voltage-gated sodium channels. That depolarization will reach its peak and sodium channels will close. Within a short period of time, calcium channels will open as well as potassium channels. All right. Now on the next slide, and these slides the ones I uploaded on Friday, I go through this step by step, and I talk about two different types of potassium channels. Don't worry about those. Okay? I'm not going to be picky about when they close and when they open. So, just to make things a little bit easier here. So we have potassium channels opening and calcium coming into the heart. But notice, even though calcium is coming in, our membrane is actually decreasing. It's becoming more polarized. It's repolarizing. So we're losing sodium at a higher rate than we're gaining calcium, since our sodium channels closed and our sodium-potassium pumps are now working. In addition, potassium channels now open. These are identified as slow calcium channels in comparison to the autorhythmic cells. And potassium channels open. Now these two channels are at cross purposes. So calcium's coming in while potassium is leaving. And while that occurs, we see almost a flat line without much repolarization and certainly no depolarization. Okay, and that's due to that counter effect of the potassium leaving. So potassium exits. We see this plateau, all right? Then those close and different channels open and these open again, but we're not going to worry about that. Essentially what happens, the calcium channels close, the potassium channels remain open, and we see a rapid repolarization. And we return back to our resting membrane potential. So the key difference between this and the typical action potential we talked about last semester is the addition of the calcium channels creating the plateau. Yes?
So you said when it comes down, the calcium closes?
Yeah, calcium closes about here. And then we have potassium still remaining open. So this entire component here is the action potential, okay, with our depolarization and our repolarization. Remember I talked about, I compared this to skeletal muscle. I'll come back to this slide. Here is the action potential of a skeletal muscle in blue. It lasts about 2 to 3 milliseconds. The action potential of a cardiac, it says 500, but other places you'll read about 300, so about 100 times longer than the skeletal muscle. And if we look at the amount of time it takes for contraction to occur, in the skeletal muscle, the action potential is already over with by the time our muscle cell is relaxing, even while it's still contracting. So here's the contraction, then our muscle cell, the action potential. So we can do technique. We can stimulate a skeletal muscle to contract again before it's completely relaxed because it's already through its action potential. It's past the absolute refractory period. And so we can continue to stimulate skeletal muscle before it completely relaxes. And that's when we saw this effect. This is the contractile force, not the action potential, where we had it incomplete or complete technique. Again, measuring contractile force, not electrical current. And so this would not be compatible with life if your heart were to go into technique. Yes?
What causes heart palpitation?
Heart palpitations are usually it can be either a premature ventricular contraction or it can be a rapid hard beating. So when my son had his problem at school last March and fainted, he said he could actually, when he was taking a shower, he could actually see his chest moving. Those are greater contractile forces. It can be drugs, it can be changes in CO2 levels. There's a variety of things that can affect the force of the ventricular contraction, not just the rate. So it usually requires additional calcium ions, and we'll talk about this with cardiac output. But with the heart muscle, remember it's skeletal muscle, what was the source of our calcium ions? Sarcoplasmic reticulum. With heart muscle, it's sarcoplasmic reticulum, but it's primarily extracellular calcium. So when those channels open and additional calcium enters the cell, it's going to contract harder. Okay? But we'll actually look at that for just a brief period of time here. So here is a diagram of what's happening in the contractile cell. Very similar to skeletal muscle with a couple of key differences. So in skeletal muscle, we had a motor in place, in which acetylcholine bound to receptors and opened ligand-gated channels, and we had to create a threshold potential. In the case of contractile cells, either contractile or the original autorhythmic cell, the current is passing through the gap junction. That's why we don't see a graded potential. That current spreads through along the cell membrane. There's less developed transverse tubules because most of the current is coming through the gap junctions. But we still use that current to open voltage-gated channels in the sarcoplasmic reticulum. Here's another difference. Calcium channels are open in the plasma membrane. All right, so we have those two sources of calcium ions in skeletal and cardiac muscle cell. But the effect is the same. The calcium binds to troponin, which separates from the actin filament. Tropomyosin moves deeper into the grooves between the actin proteins. That exposes the binding site for myosin heads. Myosin is already cocked, binds to its head. The energy causes the head to swing forward. ATP binds to that, it separates, the energy is used to recock, and as long as there's a space available, it'll bind to another head. Okay? When the muscle cell relaxes, calcium is pumped back into the sarcoplasmic reticulum. In cardiac muscle cells, it has to be pumped out of the cell as well. Okay? Now, we talked about the control of the sympathetic nervous system on heart rate and the control of the parasympathetic nervous system on heart rate. On contractile cells, atrial contractile cells have receptors for both acetylcholine and norepinephrine and epinephrine. Increasing the force of atrial contraction really doesn't change the overall effect of the heart's function. With ventricular contractile cells, there are only receptors for norepinephrine and epinephrine. So the parasympathetic system does not have a role in changing the force of the heart's contraction directly. It can slow it down, okay? It can slow down the heart rate, but it's not going to make the ventricular muscle contract less effectively. Sympathetic will make the heart contract, the heart contractile muscle contract more strongly, and it does so by opening those calcium channels. So with more calcium channels open, more myosin heads, we're going to bind, more binding sites are available on actin. Okay. Not only that, and I'll remind you about this when we get to cardiac output control, but it also activates more calcium pumps. And so when the heart is relaxing, the calcium is going to be pumped out faster. Therefore, the heart can recover faster and be ready for another contraction. Okay? So sympathetic, norepinephrine, and epinephrine are more important when we get to controlling contractile force. So this has to happen for the heart to relax. The calcium has to be pumped back into the sarcoplasmic reticulum, and the calcium has to be pumped back out of the muscle cell. So because of that, I talk about some of the drugs that affect calcium pumping, but again, we'll look at that when we look at blood pressure, because those same drugs, if it's going to make the heart pump more efficiently, it's going to slow heart rate down and maintain blood pressure. What would a calcium channel blocker do to blood pressure? It blocks calcium channels from opening. It's going to decrease blood pressure. Okay? In addition, obviously, we can control blood pressure by controlling blood volume. So there's a bunch of different things we'll look at when we get to that point. So when I recorded those, when I uploaded those new slides, I deleted, unfortunately, the rest of the slides on my PowerPoint thing. I have two sets. I have the ones with the clicker questions, and I have the ones I put up on D2L. And so I was working with my clicker question ones, and I deleted all of those. So I have to go, the rest of these slides don't have clicker questions on them. At least I still have them. I just have to recreate the wheel. All right, so before our first break now, let's look at the ECG, electrocardiogram. It can be referred to as ECG or as EKG. So this is on page 38 of your lecture notes. It's still spelled the same, electrocardiogram. It's a tracing of the electrical current pattern through the heart. The K is just easier to differentiate, and EEG is an electroencephalogram tracing brain waves. And so sometimes EEG, ECG, it can be difficult to clarify. So because cardio has a hard C sound, EKG is sometimes used, but it's still referring to cardio. Okay? So as I indicated, instead of today, we'll do the EKGs first thing on Thursday morning before we start lecture. We have multiple components available, so it will take less time. But I want to go through what these mean. And so when we look at an electrocardiogram, a tracing, most of you are familiar with these from either seeing them in the hospital or on medical shows. And it runs through on an oscilloscope. It just goes over and over and over and over. All right? So what's happening? When we see a straight line, the heart is not dead. All right? Oh, it's not even a straight line here. Let me draw this here. I don't like sliding lines. So what is happening when you're looking at an ECG, and that's all you see. When the ECG is taken, when we do the ECGs on Thursday, you'll put a ground electrode on your leg and a lead on each wrist. And what you're doing is comparing the electrical changes as the current flows through the heart muscles to the electrical current number of ions that are already present in the skin. So it's a measurement of the direction in which the current is flowing in the heart in relation to where it is in the skin. We're going to be doing 3 leads. Not most, but many of the medical ones can do 12. I still remember when I was working in newborn nursery, they wanted to run an ECG on a newborn, and they brought up an adult machine, and they were trying to put 12 leads on this little 5-pound baby. But typically, again, we're not, the action potentials that we were going through, those are recorded by actually placing electrodes inside the muscle cell. So it's a recording of the change in electrical current in one cell. An EKG is a measure, a comparison of the current in the heart to what's in the skin. All right, so we're seeing the overall change in depolarization and repolarization of the heart rather than one specific current. And again, what's happening in the skin. So when we have a flat line, what that is telling us is that there is no depolarization wave passing through the heart. Neither the atria, contractile cells, or the ventricular contractile cells are depolarizing. What is depolarizing? Is there anything depolarizing in the heart when both the atria and the ventricles are relaxed? Exactly. So during this straight line, when the ventricles and the atria relax, the autorhythmic cells are going to be depolarized. That's not picked up on the EKG. Okay? The autorhythmic cells reach threshold and fire an action potential. That wave passes through the gap junctions of each of the atrial muscles as a wave of depolarization through the atria, and we see that in our first deflection, which is the P wave. This is not depolarization and repolarization. This is reflecting a wave of current towards or away from where the electrodes are on the skin. So all we can say about the P wave is that it is indicative of, caused by a wave of depolarization through the atria, through the contractile cells of the atria. Right? This itself is, again, not depolarization and repolarization. This is a deflection caused at the electrode at the skin by a wave of depolarization through both atria. Then, we see a flat line again. If we were to look at the autorhythmic cells, this would be what occurred at the autorhythmic cells, resulting in a contractile cells in the atria doing this. So this would be one atrial contractile cell. So it's going to depolarize. But again, it's all of them creating the P wave, right? Then we see the ventricles contracting. And when a wave of depolarization occurs in the ventricles, we see several waves. This is identified as the QRS wave. And this is caused by depolarization of the ventricle contractile cells. So this is due to a wave of depolarization through the ventricle. Again, we're looking at the difference in electrical current in the heart versus what's at the skin, the number of ions at the skin. This is not a measurement of contractile force. Remember when we talked about muscle? We drew diagrams that showed the contractile force. This is not contractile force. Because of the P wave, the atria will contract, but it's not the contraction causing this. It's that wave of depolarization. So what's happening here then? Atria depolarized here, ventricles depolarized here. What's happening in between? So we start to see the P wave as that depolarization is moving through the atria. What happens at this point? Does that wave depolarization continue? No. Within the valve, there is enough connective tissue that's non-conductive that it forms a structure known as the cardiac skeleton. It's really not bone. It's just collagen fibers, which are not conductive. And that stops that wave of depolarization. The AV node is depolarizing on its own, but it reaches threshold more quickly because of the current from the atrial cells. It depolarizes, causing the bundle to depolarize, causing the bundle branches to depolarize, and then we reach via gap junctions the ventricular cells. So the time period, the lag period, the atria are no longer depolarizing, ventricles have not yet depolarized, so this interval known as the PQ or PR interval is the time that takes for that conduction to reach from AV node to ventricular muscle cells. Okay? So when you measure it on the machines, the beginning of the P to the R or the beginning of the Q, and this is known as the PQ or PR interval.
Can you define it again, please?
Yeah, I'm going to write a definition on the board. So this is the period of time required for conduction of, well, conduction through, let me rephrase it, for AV node to conduction myofiber depolarization. So if there is some damage to the AV node, as we'll see in a moment when we talk about heart block, that is going to take a longer period of time to occur. Okay? It may take so long that we never get a QRS wave. We have to wait for the next SA node to fire. That's described as complete heart block. Obviously, eventually it has to get through or you're dead, but it can take a variable amount of time. All right, so we have P wave, the PQ interval. Now at some time, obviously, our atrial cells are repolarizing. That is masked by the QRS wave. So in our ECG, we never actually see any deflection caused by the repolarization of the atrial cells. However, we do see the repolarization of the ventricular cells. And that's P wave. So a wave of repolarization through the ventricles. And then we start all over again. Okay. So if we look at, can I erase this now? You guys have that? So I'm going to come back to the ECG in just a moment. Okay, I'll keep harping on action potential. So if we're just looking at the autorhythmic cells, we're going to see something that looks like this. autorhythmic cells reaching action potential and causing a wave of depolarization in the atria. So ignoring the rest of the ECG, if we had no ventricles, this is what our ECG would look like. In response to the action potential, the P wave depolarizes. In response to the action potential of the autorhythmic cells, the P wave depolarizes. Okay? So this causes the atrial cells to depolarize. That results in the P wave. Okay? So we could lay on top of that our atrial cells doing this. Because that's what triggers this, is the depolarization of the atrial cells. Now, let's ignore the P wave, okay, and look at the QRS wave. Again, this is showing one cell rather than the whole atria. Okay? So can I erase this now? No words of protest? All right, so we look at ventricular effect. One ventricular cell is going to depolarize. So that's ventricular contractile cell. What's going to happen on the ECG? Depolarization is going to result in the QRS wave, repolarization in the T wave. All right? Depolarization results in the QRS wave, repolarization in the T wave. Now I'm kind of forcing things together because, again, this is the whole ventricle. This is a single ventricular muscle cell. Okay? But as this happens through all the ventricles, it causes this appearance on the ECG. Remember, this is having an electrode in one single cell. This is comparing the entire heart to the skin. We're trying to give you an idea of what's happening. Question?
Well, on the last one, the P wave.
The P wave comes after the autorhythmic cell and occurs with the depolarization of the atrial cell. And we don't see the repolarization. So this rise right here is the depolarization, which is the P wave. We never see the repolarization. On the ventricles, the depolarization is the QRS. The repolarization is the T wave.
That's what I was getting my, but
Yeah.
it wasn't, I was thinking that was the P wave.
Ah, okay. Let me put the labels back. Let me make sure.
Sorry. My brain was just spinning in circles right there.
That's okay.
Now
It
it
happens.
makes complete sense. Like, get my letters wrong.
So on Thursday, when we look at the lab, you'll be measuring this for yourself, or if you don't want to do it for yourself, you can use the data from a group member, but it's always kind of fun to see what your own heart is doing.
I'll break that machine. I'll let everyone try it out.
And then we can use on the strip machines, there's each little graph represents the distance, represents 0.2 fractions of a second, whereas on the computer, you use a little I-beam bar, it'll measure it, calculate it for you. Okay, but I want you to be able to know how to use the graph strip. So when the heart rate increases, this distance from here to here is when the heart is resting. If we have a faster heart rate, it's not the PQRS T wave that changes, it's the T to P. So during this period of time, both atria and ventricles are relaxed. And that's what increases or decreases as heart rate increases or decreases. It's not this component. Okay, it's the relaxed period. And you'll see that when we, a little bit better when we talk about cardiac output. Okay, so before break, let's look at some ECG changes.